Hi everyone, in this video we're going to continue our work in the preliminary example for section 8.5. So here we're going to look at part B of that example. So part B says below are graphs of the function f of x equal e to the 2x, together with the following polynomials from part A. So before looking at that, let's just recall that series that we found in part A, p of x. So I'll just write that out here. So we found that p of x, using our technique for finding each coefficient, was equal to 1 plus 2x plus 2x squared plus 4/3 x cubed plus 2/3 x to the 4th. And I went ahead and computed the values of the coefficients that we found just to kind of simplify our work here. But feel free to check me on that as well. All right, so there was our series p of x. Now let's consider these polynomials, p sub i's down here. So we have p sub 1, which is 1 plus 2x. P sub 2 is 1 plus 2x plus 2x squared. P sub 3 is 1 plus 2x plus 2x squared plus 4/3 x cubed. So notice what's happening with each of those p's. So for p1, we just have the first two terms. P2, we have the first three terms. P3, we have the first four terms rather. But notice where the indices align, or why it makes sense to label this first one, say P1. Well, recall our coefficients were C0, C1, X, C0, C1, C2, C0, C1, C2, C3. Also notice the exponents of our x terms. So for P1, our largest exponent of x is 1. P2, the largest exponent is 2. So we're looking at a 2-degree polynomial. P3, we're looking at largest exponent being 3, so a 3-degree polynomial. So that's where the indices that we have here come in. All right, so now what is it doing here? It says label the graphs of P1, P2, and P3 in the diagram below. So let's go ahead and highlight some of what they've already done for us. So in each of these graphs, we have graphed, or the book has graphed for us, the function f. So that's that function that we started with, e to the 2x. So now let's go ahead and determine on our graph which is corresponding to each polynomial. So notice p sub 1 has just a linear factor, so meaning there's no exponents. So it would make sense then that P1 is going to be that first curve here. So here must be P1. And then we see here that as we continue going, the next graph is going to be P2. And we're going to get P3. So let's just take a moment to pause and look at what we can observe about these P1s, P2, P3, and how they relate to F. So what we should observe is that as the index here, P1, P2, P3, increases, our polynomial approximates our function more and more. So let's go ahead and write that down. So the P1, or rather not the, but right up here, P1, P2, P3 gets in some sense closer to F, right? So if we want to formalize that, we can actually say that the sequence of P's converges to our functions. So if we kept on doing this, looking at P4, P5, etc., we notice that all of those p sub I polynomials converge to our function. So I'm going to write that down. The sequence, we have a sequence of polynomials, P1, P2, P3, etc., converge to f of x equals e to the 2x. And maybe this isn't too surprising because that's how we built these polynomials. That's where these coefficients come from, was assuming that we're equating our series of p of x to e to the 2x. So then if we're taking partial sums by just looking at part of those series, then that should converge also to the P of X series that we computed in part A. But maybe what's super cool about this is that we can find a series that is equal to our function. And if we don't want to write the whole infinite series, we can approximate our functions by using one of these partial sums. I'm just going to say that we can approximate a function with a series. Very cool. So now that's going to lead us to the main definition of this section. So it turns out what we just computed in parts A and B of this preliminary example is called a Taylor series. So this P of X here that we've computed is known as a Taylor series. And it turns out this form for the coefficients is a general form. We used our function for f of x equaling e to the 2x to find those specific coefficients, but the same form works to compute the coefficients in general. But let's take a look at that definition to formalize it a bit more. So here's our definition. So let f of x be a function, then what's called the Taylor series for f of x centered at a, which we'll get into what that means here in a little bit, is given by the formula p of x equals the sum from n equals 0 to infinity of fn, or the nth derivative of f, evaluated at a, divided by n factorial times x minus a to the n. So if we were to write those terms out rather than writing as a summation, they would look like the following. So when n equals 0, well, then we just have the function itself. So f of a over 0 factorial times x minus a to the 0, which would just become f of a, which is what we have here. And then you can check the remaining terms. When n equals 1, we have the first derivative of f evaluated at a divided by 1 factorial times x minus a to the power of 1. So recall in our example in part A, we saw similar forms here in these coefficients. So you can look back at that formula that we found. We found f, or ith derivative of f evaluated at 0 divided by I factorial. So that's exactly what we did, but we were just using a equals 0. So we were looking at C0 is f of a, C1 is f prime of a divided by 1 factorial, etc. So we've seen these coefficients before. So what we did in part A works in general. Even more generality in that we can center our polynomial, or our series rather, because we're looking at a Taylor series, about any given value or constant a. Where does a come in? Well, notice in this graph that we looked up above, where do these polynomials match our function exactly? They match exactly when x equals 0. So our series is centered at 0, which means that our function and our finite polynomials match up exactly at x equals 0. But if I wanted them to have matched at, say, like 1, then I would have looked or computed that Taylor series for f of x centered at 1. And we're going to see some examples to make that a little bit more concrete. Okay, but let's finish and continue this definition. So if we just look at the sum of the first n terms of the series, so let's call that p sub n. And this isn't necessarily the nth terms, it's like the nth plus 1 terms, recall, because our first term has a 0 coefficient. So that's kind of a subtlety here. So maybe I'll say this is not n, it's n plus 1. Or look at the x to the n. That's kind of the highest term we're looking at. Then that polynomial that just goes out to the x sub n, or x to the n term, is called the nth degree Taylor polynomial of f of x. So that is, if we want to be real explicit, P sub n of x is equal to f of a plus that first term plus etc. all the way to that x minus a to the n. So we'll just finish here with a note. So in our example, in example part A, we had P of x equals f of 0 plus f prime of 0 over 1 factorial times x plus f second derivative evaluated at 0, 2 factorial x squared plus third derivative of x evaluated at 0 over 3 factorial x cubed, etc. And again, as we looked at this definition, this is the general form for a Taylor series. And in this case, our Taylor series was centered at x equals 0. And so what does that mean? This means Pi at 0 is equal to f of 0 for all I, meaning our polynomials, any of the nth degree Taylor polynomials aligns with our function at 0. So it turns out these types of Taylor series centered at 0 are quite common. In fact, they're so common that another mathematician coined their name, and that was Maclaurin. So often when one of these Taylor series is centered at 0, or when a equals 0, we call the series a Maclaurin series for f of x. And it has the following form that we already wrote out. So it has this form here. In that form, we just obtained by plugging in x, or a rather, equals 0. So that's just some more language here, not a new concept outside of a Taylor series definition. All right, great work going through the rest of that example and looking at this definition. In the next videos, we're going to look at some more examples to get us more familiar with this concept.